Good afternoon, everyone. I'm Leslie Zane with the Tech Museum, and I'm so delighted to see you all here today to hear about algebra. And I don't think anyone was more surprised than Keith was when he found out this event was sold out. So congratulations on getting a ticket to this event. A couple of housekeeping items. Please shut off your cell phones. And some of you were given index cards, and those are for questions that will be asked during the conversation that Keith will have with Angie after his presentation. If you didn't get a card and would like to ask a question, just raise your hand after the presentation and I'll deliver cards to you. And I just want to go over some of the materials that were left on your chairs. There is a survey. If you wouldn't mind filling that out, that would be great. It will help inform us what other speakers we should book in the future. Also, as you can see, this event sold out, so we encourage you to buy tickets for the upcoming events as soon as you can. Also, the Islamic Science Rediscovered exhibit will only be here for maybe another month and a half. Do not miss this exhibit. And because of this exhibit, that's how we ended up with this speaker series and how we got to the sold-out event. So all things are related. And lastly, Tech Awards 2012, the nominations are now open. If you go to the Tech Awards website, you can nominate an organization or yourself, or if you're part of an organization, please go to the Tech Awards nomination site, and you'll see that we added a new category in 2012, Sustainable Energy, the Sustainable Energy Award. So please check that out. And I think that's all the housekeeping stuff. So, today's topic, the birth of algebra, we'll present it in a slightly different format. Keith will talk for about 20 minutes and catch us all up to speed on algebra. 20 minutes, we'll know everything. And Angie will take it from there. And then Keith and Angie will have a conversation. I'm sure most of you are now familiar with Angie Coiro, our award-winning journalist and moderator, and you've heard her on NPR, Air America, live from the left coast, Your Call on KALW, KQED's Friday Forum, and KGO Radio. Now, Keith Devlin. Dr. Keith Devlin is Executive Director of HSTAR, the Human Sciences and Technologies Advanced Research Institute at Stanford University. He's co-founder of Stanford's MediaX Research Network, which explores innovation for measurable improvement in the productivity of people who work with information. He's also a senior researcher at the Center for the Study of Language and Information, CSLI. Keith is a World Economic Forum Fellow and a Fellow of the American Association for the Advancement of Science. Among other projects, his current research is focused on the use of different media to teach and communicate mathematics to diverse audiences. He also works on the design of information reasoning systems for intelligent analysis. He has written 31 books and has published over 80 research articles. His latest book, Man of Numbers, is on sale at the bookstore. If you're a member, you get a discount. If you'd like to buy the book, Keith will be happy to sign them for you. He's also the recipient of the Pythagoras Prize, the Peano Prize, the Carl Sagan Award, and the Joint Policy Board for Mathematics Communications Award. In 2003, he was recognized by the California State Assembly for his innovative work and longtime service in the field of mathematics and its relation to logic and linguistics. And foremost, he's also known as the math guy on NPR. Won't you please welcome Dr. Keith Devlin.
Thank you. Okay, so the reason I wanted to begin with a little presentation was that in my experience, very few people actually know what algebra is. That despite the fact that it's obligatory to teach it in the schools. So I'm going to tell you what algebra is. First of all, it's not arithmetic with letters. Whatever my grandfather used to claim, that's not what it is. It's actually a way of thinking, and it's a different way of thinking from arithmetic. In fact, a lot of the problems kids have in the schools is that they don't realize it's a different way of thinking, and they keep trying to solve problems with arithmetic when you need to stop doing arithmetic, and do something else. It doesn't require symbols. Okay, that's not what it's about. any more than arithmetic requires symbols or music. We all know that music doesn't need symbols. You can play music without reading music. And we sort of know the same is true of arithmetic, because you can do arithmetic without a paper and pencil, and you can just do it in your head. But people sort of somehow think that algebra is inherently symbolic. It's not. That's just a technology. It's a way of representing it and manipulating things. Okay. In fact, modern symbolic arithmetic done with symbols, that began in India and Syria between 200 and 700 current era, used extensively in the Arabic-speaking world in the 8th and 9th centuries, and then moved across the Mediterranean into Europe starting in the 13th century, first in Italy, then moving up and north and westwards, and then sort of eventually taking over the whole world. Okay. Symbolic algebra done with symbols, that's very recent. That was invented in France in the 16th century. Francois Viète, and then a century later, René Descartes brought the idea of doing algebra symbolically. So we need to first of all realize that it's a way of thinking, an incredibly useful way of thinking, and it's not about symbols. Symbols was just a technological issue. It was how do you represent it on a piece of paper, or parchment, or blackboard, or whiteboard, or a computer screen. Okay. So let me just give a few bullet points to sort of distinguish algebraic thinking from arithmetical thinking. First of all, algebra is logical thinking, as opposed to arithmetic, which is numerical thinking. So if you're doing arithmetic, you reason, you calculate with numbers. Numbers are the things you're working with. If you're doing algebra, first of all, you're reasoning logically, and you're reasoning about numbers, rather than with numbers. Okay. If you're doing arithmetic, the reasoning is quantitative. It really is about the size of those numbers. Algebra is qualitative reasoning about numbers. And a key feature, I should actually at some point distinguish the fact that mathematicians use the words arithmetic and algebra to mean something very different. Okay? If you go into the university at Stanford and you've pulled books off the shelves with the word arithmetic or algebra in the title, you're not going to get what we're talking about here. This is something very different. So I'm using the words arithmetic and algebra in the historical sense that they were used in the 8th, 9th, 10th centuries onwards, and in the sense that people associate it with those words in the high schools. So it's essentially school algebra. Okay. And one feature of that is historically this is an important distinction. You have a name for an unknown, and you reason logically to find its value. Substituting numbers in a formula, which is what many children and adults try to master in order to do algebra, isn't algebra at all. If that's what your view of algebra is, you're never going to be able to do it. That's just arithmetic with formulas. Okay, so we need to realize that algebra is a very different way of thinking, and it evolved over many centuries. This was a long struggle of our ancestors to develop this powerful tool called algebra. And incidentally, I'm going to give you later on the answer to the perennial student's question, what is algebra good for? And that answer is going to come out of the first major textbook on algebra that was ever written in the 9th century. So we're going to go back to the source to answer the question, what is algebra good for? Okay. Example. This is what most people associate with algebra, and that's fine because even historically these were the kind of problems that people developed algebra to solve, quadratic equations. One way you could solve that one is just look at it and say, it's about fives, 10s, 15. Just trial and error, and it doesn't take long to solve it that way. In fact, if you're a teacher and you have a kid in your class who's really good at arithmetic, that child will be able to solve that. In fact, one of the problems if you're a math teacher is that the kids who are good at arithmetic are often slow at learning algebra because they can get by a long way with just using arithmetic. Their skill in arithmetic carries them forward until they realize that there's something else going on in algebra. Another way you might solve it is by plugging the numbers into a formula, and many of us learned this formula in order to pass a test at school. I did. That's arithmetic, that's arithmetic. There's no algebra going on here. It's just arithmetic with letters and formulas. On the other hand, there's another way that some people may remember learning to solve a quadratic, which is you manipulate it and you maybe have to complete the square, and then you factor it. Now that's algebra. Okay, so there's some algebra. Although it's worth noting that the unknowns that you're reasoning about are A and B. It's not the X that's making it algebra, it's the A and B and the reasoning used that makes this algebra. But this is algebra. Okay. When did it begin? Well, it's easy to sort of categorize history when you look back. And when we look back, knowing what we know now, we can see that the ancient Babylonians, way back in around 2000 BCE, were sort of doing algebra. They were doing algebraic thinking. And we get that evidence, there's thousands of clay tablets been discovered with cuneiform writing on them. About 400 of them or so have a lot of mathematics on them. And that mathematics described how to solve geometric problems involving lengths and areas of figures, which actually could relate to commercial problems as well. It was just geometric, it was a way of thinking about many kinds of problems. It wasn't just about geometric figures. It was a way of thinking about quantities in general. And then, in fact, some of the problems just seemed to have no practical application. Others were very, very practical. But the way they described them, although those problems were described in terms of specific numbers, if you look at the way they were described, it was clear that they were saying, these numbers are just general. It's like saying, take 2 eggs and a cup of flour and so forth. Everyone knows that you could take 4 eggs and 2 cups of flour. You can scale it up and down. Recipes written in terms of specific quantities, those are just meant to be placeholders for general quantities. Okay. So these were recipes written in terms of specific numbers. So it's the beginning of algebraic thinking, because they were clearly recognizing that this was not about the particular numbers. So it was expressed in terms of arithmetic, but it was clearly reflecting algebraic thinking. In fact, some of the tablets, we really do see algebra in the following sense. They introduced an unknown. It wasn't an unknown number, it was an unknown length. And then they performed geometric operations on that unknown length in order to determine the length. This is algebraic thinking. We perhaps ought to call it geometric algebra. But in terms of that feature of algebra I mentioned about introducing an unknown, which is really one of the characteristics we have to apply to see as algebra evolved throughout history, the Babylonians had it 2000 BCE. And in fact, they used these kind of methods to solve some problems that we would regard as arithmetic problems. As arithmetic problems about numbers. Let me just give you one example of the kind of problem they would solve. And they, by the way, express numbers in base 60. I'm going to translate it nicely for you in terms of decimal. So I added the area of my 2 squares, 1,525. The side of the second square equals 2/3 of the side of the first, and another 5 more. And they gave a step-by-step solution to that problem that was geometric. It's equivalent to the algebraic problem of solving these 2 equations. Quadratic and a linear in 2 variables. That's pretty sophisticated, right? Similar problems could be solved by the Egyptians, amongst others, the Chinese, and I've listed some of the more famous sources. The Egyptians from evidence in the Rind Papyrus, the Chinese from a very famous book called The 9 Chapters of the Mathematical Art, and the early Greeks, like Euclid's Elements. They could solve problems like that too, but you can't really identify algebra in what they were doing. It's just they were more rooted in arithmetical procedures and logical procedures. This idea of having an unknown and reasoning about it can't really be discerned there. These are fine distinctions, and scholars do actually argue about whether you call it one thing or another, but I'm trying to trace a development that happened gradually over many centuries. The way that these authors wrote in the more geometric ones is, instead of doing something that was like an equation or an identity like the one on the top, they would draw a diagram and reason geometrically. So it was very visual thinking rather than sort of logical algebraic type thinking. But they were getting there. They were solving the problems in their own way. Okay. We first see really recognizable algebra in the work of Diophantus, who wrote a multi-volume work called Arithmetica, and don't be fooled by the title, this is definitely algebra. He introduces unknowns and reasons logically to find its answer. Diophantus actually lived not in Greece, He lived in Alexandria, in Egypt, between around 150 and 250. And there's a relatively recent manuscript cover for his book, Arithmetica. He used letters to denote things, but I've already said that symbols are not what algebra is about. That's not characteristic of algebra. But he did actually introduce letters to denote things. He also used negative numbers in calculations. This was one of the first people that did that. By the way, if you go online, and I went online when I was preparing this talk and found various sources on Wikipedia, the sources on this are incredibly unreliable. It's one of the few places I've found where Wikipedia is not a good source, and I know that because I know some scholars who work in this area, and I consulted them, and they basically said, forget anything you can find online. Most of that is based on 19th century scholarship, which was done in good faith at the time, but has subsequently been overturned. So more recent scholarship, particularly over the last 20 or 30 years, has found out a lot. And I'm going to draw on some of that in these remarks. Okay. One of the things Diophantus did was show how to solve equations, quadratic equations, using something called a technique called restoration and confrontation. You're going to hear quite a bit about that, including the origins of the word algebra. More or less, and this is very vague because this is a 21st century perspective on something that was very different in medieval times and earlier. Restoration is it sort of corresponds to moving things from one side to the other and changing the sign. And confrontation corresponds to removing like terms from both sides. Now, the reason that's misleading is because they didn't have negative quantities in their equations. And they didn't reason with negatives, they did something different. And you have to understand what they were doing. And in fact, the terms restoration and confrontation, those English words do reflect what they were actually doing once you understand what they were doing. But those are just analogues today of ways we manipulate equations. They were doing something different because they conceived of those things differently. And he managed to solve equations up to 6-power equations. So this is powerful stuff. Okay. Jump forward a few hundred years. In India, we have Brahmagupta writing a book, which I won't attempt to read the title, but you can read it for yourself. It more or less translates as correctly established teachings of Brahma. This is where zero first appears. And it's a book about arithmetic as much as anything, but there's recognizable algebra. And in particular, it's where we find the first complete solutions to quadratic equations. So looking back with the lens of history, Monday morning quarterbacking, we can see algebra appearing right back then. But if you want to really see, and this is why this is in this series, if you want to really see algebra coming full-blown, you have to begin with this guy. And we're now going to be talking about what I'm going to use. I'm going to use the term Arabic mathematics and Arabic algebra. Apparently I'm not the only speaker in this series who was a little uneasy with the name of the series, Muslim science, because science is universal. It's one of the disciplines where everybody in the world works together. And I'm going to use the accepted scholastic sense of referring to the main texts, like Latin texts, Greek texts. We speak about Greek mathematics, although many of the people who did Greek mathematics lived in Egypt, for example. And then there was a period when most of the texts were in Arabic, and then Italian and Latin and things. So I'm going to use that. So when I talk about Arabic algebra, I mean algebra done by people where the scholastic language was in Arabic. Okay. And that tradition, one of the first major books, was written by Al-Khwarizmi, whose name, by the way, gives us our modern word algorithm. One of the things he did was write a book that describes how you do calculations with Hindu-Arabic numerals, and from his name, Al-Khwarizmi, we get the word algorithm. He lived around 780 to 850, and he wrote he wrote many books, but the two most famous books was he wrote a book around 825 on how to calculate with what we now call the Hindu-Arabic numerals. The symbols 0, 1 through 9, and all of the familiar algorithms we learn in school. He wrote one of the first books, and certainly the first major book on that led to the modern world. And then a few years later, he wrote another book, part of the title of which is that phrase, algebra. And there we get the word algebra. And we take that word because this was really the first modern recognizable book on algebra. The symbolic stuff still hadn't come. This was written in words. So it's not about the symbols, but we definitely see a book on algebra. And in fact, we're about to go into a period where over 1,000 books were written on this. This is huge. This was an outpouring of creativity and scholarship as the world has never seen before. Okay, roughly speaking, that phrase algebra or muqabala means restoration and confrontation. Those two terms we saw in connection with Diophantus. Roughly speaking, or more, a sort of a crude but somewhat literal translation for the book would be the abridged book on calculation by restoration and confrontation, or in modern terms, the abridged book on algebra. He was asked by the Caliph to write this book and to write it for ordinary people. Okay, this was meant to be a very accessible book. One of the reasons I'm interested in people like that is I struggle to write accessible books. And I see in this guy and a few others the same instinct to write books that ordinary people can read. And so these guys are my heroes and my models, my role models. And he was the guy, and so this is really the first real modern arithmetic textbook, algebraic textbook, this book on algebra. And here we find in his introduction, what's algebra useful for? And here's what he says. What is easiest, and so the book is about what is easiest and most useful in arithmetic, such as men constantly require in cases of inheritance, legacies, partition, lawsuits and trade, and in all their dealings with one another, or where the measuring of lands and digging of canals, geometric computations, and other objects of various sorts and kinds are concerned. This was practical stuff. In fact, a characteristic of that entire period that we call Arabic mathematics is it was driven by practical considerations. This was engineers. These people were engineers, they were traders, they were commercial people. They didn't recognize algebra as a discipline. It was a collection of useful tools to do things in the world. Remember, go back at that time, Baghdad was the equivalent of San Jose. It was the technology capital of the world. That's where everything was happening in algebra, arithmetic, mathematics, technology. It was practical stuff. It was about engineer, commerce, and trade. And everything was driven by that. So, in this location, we can identify with what happened in that part of the world then. There's a page from that book, and a summary of what you'll find in there is a complete classification of all the kinds of linear and quadratic equations, and you have to classify them this way because you don't have negative coefficients, so you have to organize them differently. And having classified them, he shows how to solve them. So you've got a systematic study of quadratic equations, and I'm not going to read through this, but this is what it looks like. This is an English translation of one of his examples. This is how to solve a quadratic equation, not a symbol in sight. This is how they wrote it. It was a story. They were telling a story about numbers. It was a script, but no symbols. You may have, if you look at the problem at the beginning, you may have already had time to figure out that he was solving that quadratic equation. You take the number 10 and you split it into x and 10 minus x, you square 1, you multiply the other by 81, and he solves it. And that's the solution. So the first two lines is the problem, and then there's a solution. And that's how it was written out. Written in writing. I should make a comment, because if you go to one of these public sources on the web, you'll read many people saying things like there was a period of rhetorical algebra and literal algebra. Well, that's not true. When they solved problems, they used symbols. They used to write in a dustboard and they put symbols down. Now, of course, we don't have the historical evidence because it was on a dustboard. They didn't do it this way. This is how they described the answer. They actually did reason symbolically. Relatively recent scholarship has determined that. So algebra was done symbolically from the beginning. There was no separate period of literal algebra and rhetorical algebra. It's just how it was described. but they certainly wrote it down in words. Okay. And then we come to this period of enormous activity that took place in the Muslim world, beginning in the 9th century, 8th, 9th century, and for the next 300 or 400 years, we had this incredible effort where all of known knowledge on the planet was collected together, translated, studied, expanded. I mean, this huge outpouring of scholarship and activity over several hundred years, led by the caliphs, supported by the wealthy people. People poured money into that in the way we see in the United States in particular today, pouring money into scholarship. And it was an incredible period of time. It begins, at least in terms of the historical record, we identify Al-Khwarizmi as being the first with his books. But following that, we get Abu Kamil, who wrote at least 10 books, managing to solve that rather challenging-looking fourth power equation. And in fact, he looked at some other problems with what's known as indeterminate equations, where there's not just one answer. And he looked at one problem and had the perseverance to find 2,676 solutions to that problem. So this is powerful stuff. Another one in this period, Al-Karaji, he was the first person who, and this again is a modern interpretation, recognized that the exponents could be continued indefinitely. And with modern perspective, we can see that he was using induction to prove things and managed to prove this formula for the sums of cubes. And he wrote 3 books or more. We've got evidence for 3 books. Then we have someone known in the West more famously as a poet, Omar Khayyam. He was a much better mathematician than he was a poet, believe me. I appreciate poetry and mathematics, and he wins hands down on his mathematics. He was an okay poet, but a brilliant mathematician. He was a little bit unusual compared with most of the others. They were very much driven by practical considerations. Although Abu Kamil, although he wrote a book for practical people, wrote it for a more sophisticated audience. Al-Khwarizmi's book was very much for the practical people. Abu Kamil's book was for a more mathematically sophisticated group. Omar Khayyam was very much a scholar. His book was very scholastic, and it was very geometric rather than algebraic. Okay. And here we've got a picture from his book, or at least from a paper, Cubic Equations and Intersections of Conic Sections. Very sophisticated work. And then finally, I should mention As-Samawal, who was a child prodigy. Wrote over 80 books and articles. He was an interesting figure in his own right. He was born to a Jewish family. His father was a rabbi. He eventually converted to Islam. And then his father sort of cut him off, and they tried to make up, but the father died. There's a tragic human story here. But he was a brilliant child prodigy. He wrote dozens and dozens of books, 80 or more of these things, and some of them in his teens. So quite a remarkable figure. And there was this quote from his work, which echoes a quote I've already made. Algebra involves operating on unknowns, using all the arithmetical tools in the same way as the arithmetician operates on the known. So algebra wasn't recognized as a separate discipline. It was recognized as efficient arithmetic. And if you want to see what happened next, one of the books that Leslie mentioned at the beginning is my book, The Man of Numbers, which describes what happened when those ideas were picked up and transported across the Mediterranean. And then there's another book where I compare that with Silicon Valley in the 80s, and the stories are remarkably parallel. Those of us who lived here in the 80s know what it was like to have lived in that part of the world, essentially modern Iraq and what we used to call Persia, Iran. If we lived in that part of the world in particular, and then later in Italy and Spain in the 13th century onwards, we know what it was like to have lived then. The pace is different, but what goes on here, and what's been going on here since the late 70s, is what happened in that part of the world. The focus changed. It began in India, moved to Baghdad, then to Pisa, Venice, and slowly westwards. And I think it's still moving west. It's crossing the Pacific right now. So let's not think that we own this. We did own it, but it's moving. Thank you.
stuff.
And there is a blog. If you want to see more details, I've got a series of articles appearing on my blog, Prof. Keith Devlin, and there's already 2 episodes up, and everything I've said today is going to appear over the next few weeks. Angie.
We're going to take your questions throughout, so if you currently have any questions written down that we can integrate into our conversation here, just hold them up and we'll collect them. And you can continue to do that. If anything comes to your mind while we're talking, just hold up your question and someone will come gather it and they'll get them to me over the course of the conversation. So one of the things that you and I discussed briefly before we got on stage today was the fact that this is a sold-out lecture, and not only we're talking about mathematics, algebra, arithmetic, but we're doing it in the thick of the holiday season.
You bet.
We could probably get a series of answers if we polled people and said, why are you here today? But if we stipulate there's a common reason for most of these people, and we stipulate to your charm, which I'm sure is bringing some people as well.
Sure, that's all it is. It's everything's charm.
Why is today's lecture sold out? Why does this catch on with people?
I have no idea. I went online this morning and I thought, I wonder how it's doing. And it said sold out. I actually don't know.
But you're conveying math to a larger audience that might normally take it in, has brought you to NPR, has brought you to a number of places. Are you an evangelist?
Yeah, I think I'm an evangelist. I mean, part of the answer, by the way, is probably this is Silicon Valley. Our paycheck depends upon the fact that we can all do algebra. Right? I mean, this is, we use the stuff. But I am an evangelist, and for various reasons to do with my own childhood, I've always had this passion to explain things to ordinary people. I just grew up in post-war England as a regular working class kid and discovered education and discovered how that changes lives and changed my life. And if I see people that don't sort of see that window of opportunity, that doorway, I have an instinct to try and say, look, this can change lives in dramatic ways. And so based on my own life's experiences, I've always had this urge to try and arouse in others the interest that was aroused in me when I was a small child, that turned me into someone who's spent their lives reading books and that kind of thing.
We talk about the very beginning of what you presented to us, and that algebra is a way of thinking, as opposed to just a piece of arithmetic. Is that a concept that we've evolved to? Has that always been recognized throughout, that this is separate from arithmetic?
No, and in fact, the historical story, as I've tried to outline, it's only with historical perspective that we can see algebra beginning. It was really people trying to do things in the world. All of mathematics is because of people trying to do things in the world. I mean, the idea that the question, what's this good for, can even be asked is crazy, because all of mathematics was invented to do stuff in the world. Even the most abstract mathematics is invented to do the more basic mathematics, which when you unpack it, is to do things in the world. It sometimes takes hundreds of years before it filters back to the world, but it's all driven by real world considerations. Numbers themselves began because people needed money. The first application, in fact, numbers and money were invented at the same time. There is no such thing as money without numbers. Money is just numbers applied to things in the world. You attach a number and say that's worth £5 or $5 or whatever, or €5, and they're all worth quite a lot different from they were from a week ago. So money is just numbers applied to the world, and numbers were actually invented to have objects that you could apply to the world. And from then on, we've been developing mathematics, but it's all been about doing things in the world. And the drive for algebra was essentially a drive predominantly by traders, but to some extent by engineers, to do things more efficiently and to avoid repeating themselves. The modern spreadsheet, Excel, is essentially algebra. A spreadsheet to a calculator is algebra to arithmetic. Calculators do arithmetic, spreadsheets do algebra. The difference is a calculator deals on 1 or 2 numbers, a spreadsheet deals on a whole column of numbers. And the moment you talk about a column of numbers, you're doing algebra. So Bill Gates gave us all a system for doing algebra.
But if this all evolved out of practical applications, why did the concept of zero finally get named in 628? I mean, it seems like zero would be a piece of day-to-day application. I'm going to sell you 5 apples. Oh, I have no apples. Well, how did you have practical application without zero?
Well, in fact, they always did have zero, but then they were writing things in the sand and so forth, and there was always, and once they had place value, there was always a space. And in fact, the zero symbol, the symbol zero, this is only water, folks, really. The symbol zero was actually a circle denoting that there's nothing there. Something's missing. So when they had markers or scribbles in the sand, they definitely needed to record that there was an absence of something. And they knew that when they were writing it out. The zero itself is actually a sophisticated concept, realizing that the absence of something, which was important in calculations, can be recognized as the presence of something. That was a big conceptual leap. It's saying nothingness will become identified, will reify that and make it a something. So the big step about zero was saying zero is a number in its own right. Until that happened around with Brahmagupta, essentially, zero was the absence of something. And it turned out to be very powerful to make zero the presence of something. And that was basically what Brahmagupta did. And in his book, he also describes the properties of this thing called zero. It was a big step. And it was cognitively a very difficult one to stomach.
Question from the audience, why use the terms restoration, confrontation? Why do these names describe the manipulations?
Okay, so we look at something like, there was that equation with 10 minus x. Now, they didn't have negatives. So let me back up. 10 plus x was regarded as a 10 plus an x. You take an unknown and you add it to 10. That was fine. But if they had something like 10 minus x, they didn't have the concept of subtraction as such. So 10 minus x was regarded as a 10 that's lost weight. Okay, basically, if I lose weight, it's still me. I've just lost some weight, right? So a 10 minus x was a 10 that's lost weight, and it was still regarded as a 10, but it was a modified 10. In a calculation, you had to restore it to its full glory as a 10. So restoration means take this 10 minus x, which is a 10 that's been slimmed down, feed it donuts, which means add something to it, to turn it back into a 10. So it really was restoration. You did something to an equation to restore the 10 to its original glory. Confrontation means you've got this equation and there are two equal things on the same side. They're confronting each other. They're equal. They're pressing against each other. They might as well not be there. So take them away. So those terms do reflect what was being done. And it reflects the way they thought about what they were doing.
Another member of our audience wants to know, during the period that you covered, what was going on with Mayan mathematics at the time?
What was going on with?
Mayan.
We actually don't know. The scholarship isn't really there to tell us what was going on. A lot of the story that I've told today is relatively recent. A lot of the scholarship is fairly recent. And I should mention a guy called Geoffrey Oakes, one of the foremost scholars of this period in the world, who actually helped me with my book on Leonardo, although his real expertise is medieval Arabic mathematics. Geoffrey Oakes at the University of Indianapolis has been helping me a lot with this work, and he's one of the foremost scholars. And there just isn't enough scholarship to tell this kind of story yet, but hopefully it'll come around. You need to find enough artifacts. This period of Arabic algebra, there's over 1,000 manuscripts were produced, and half of those by the 15th century. So there's a lot of evidence that we can go through to tell the story and to interpret what was going on. And it depends on the information we've gotten and how the scholars have concluded things from it.
Since you brought up the name of Leonardo, can we have a little thumbnail sketch of who you're talking about and why he's important?
Yeah, well, one of the only known images is that tiny little drawing on the cover of my book. Leonardo, in a sense, is why I'm here. I'm a guy who I'm an okay mathematician, but I've made my reputation by talking about it to the general public, to explaining things to the public, going on NPR and TV and so forth, and trying to explain mathematics. And in fact, I was once called the Carl Sagan of mathematics, and I took that as a huge compliment. And so I've spent a lot of my career trying to do that. And I realized, and when I came across, there was this, and I sort of always knew about him, this guy Leonardo of Pisa, who we sometimes call Fibonacci, to give him a 19th century nickname. He was the same. He was a much better mathematician than me. I mean, you have to factor in 13th century, but he was a great mathematician. But he's more famous and had much more influence on history by writing a book. It was the book that actually two books that brought this arithmetic and this algebra from the Muslim world and brought that into Europe in 13th century Italy. And in fact, when he wrote these 2 books, one was called Liber Abaci, which was a huge manuscript in Latin, and he wrote another small version for the traders, we've actually only known the contents of that small book since 2003. I actually was able to write my book because in 2003, and this goes back to my question about the accessibility or the availability of manuscripts. In 2003, a key manuscript was found which gave us the contents of the book that he wrote for traders and merchants. When that book was written in around 1220, that little book for merchants that he wrote, probably 1210, which was a derivative copy of his big book, within a century of that book, we have, coming out of Italy, banking, insurance, accounting, double entry bookkeeping, international trading conglomerates. We have modern commercial world all coming out of Italy in the 13th century. Why? Because they got an efficient way of doing arithmetic. And it was Hindu-Arabic arithmetic that they got from Al-Khwarizmi, who got it from the Hindus who developed it, the Indian mathematicians who developed it in the first 6th and 7th century. So the key to the modern world was an efficient way of doing arithmetic. And it was incredibly powerful. First of all, it was democratizing. No longer did you have to go to someone to do the arithmetic for you, because before that was done, before people and this is a European perspective, but before people in Europe were able to do these things for themselves, arithmetic was done by counting on your fingers. They had a very sophisticated system that was accurate for numbers up to 10,000, or by using an abacus, which was a board with lines ruled on it, which you moved pebbles, and you need an expert to do it for you. And even worse, if you did your arithmetic on your fingers or on an abacus board, there was no audit trail. Impossible to base commerce on that, except commerce where it's 2 people trading goods from camels. So when the Arabic-speaking traders got this idea from modern arithmetic from the Indian mathematicians, they brought it up to North Africa on the Silk Route. Algebra was transported up through the Muslim Empire by traders, along with the arithmetic methods. Then Leonardo in the 13th century sees that. He goes to Bugia in what's now Algeria to visit his father, who was a trading representative for Pisa. Pisa at that time was the European capital of trade with the Muslim Empire, certainly on the Silk Route down to the Orient. And so, having grown up in this incredible capital of world commerce, Pisa, in the 13th century. I mean, Pisa's a kind of sleepy place today, but it was the hub of Western commerce in the 13th century. Leonardo goes to Bugia to visit his father, who's gone there to represent the Pisan traders. The Pisans had a trading house in Bugia. Sees all the Arabic-speaking traders and commerce people using this method to do trade, and based on his childhood says, this is insanely great. This will change the world. That's where the Steve Jobs comparison is. What Leonardo does in 13th century Bugia is what Steve Jobs did when he visited Xerox PARC. And he saw, you don't have to be a geek to understand this stuff if there's a good interface. Hindu-Arabic arithmetic is a brilliant interface to numbers, just as the Macintosh was a brilliant interface to computers. And just as the Mac turned computing from something that the geeks were interested in to something that we all wanted to have, you've got one right here on the table. I bet you wouldn't have used an old IBM PC in the old days. You wouldn't have done that, and I suspect you're not very good on Unix.
How'd you know?
But it's underneath there. You're using OS 10 and you're using Unix, but it has a really good interface. Hindu-Arabic arithmetic, analogously, is a great interface, and just to arithmetic. And just as those machines changed the world and changed commerce and life for everybody, so too Hindu-Arabic arithmetic changed everything in the world. And because the Italians were the first ones who got it in Europe, they began the modern world in Italy, and it spread very quickly to the rest of the world. It's an incredible story, but it is a story that we lived through in Silicon Valley.
Well, your book is an effort to, restore him to his deserved glory.
Yeah.
Ironically, as a footnote, his name is associated with a series of numbers, a phenomenon of a series of numbers that really doesn't have anything to do with them. I found that an interesting story. How did that work out?
Okay, yeah. So And it actually meets the theme because it turns out that the famous rabbit story in Liber Abaci, the problem itself about a rabbit population, the Indian mathematicians use that as an example. So too did the Arabic-speaking mathematicians. That was a classic example from the beginning of modern arithmetic, used as a good example for people to practice doing addition in Hindu-Arabic arithmetic. When Leonardo writes his book, for example, and the same would be true for Al-Khwarizmi's books and Abu Kamil's books and all of these people, their books were full of practical examples on inheritance, trade, currency exchange. I mean, all of the stuff of commerce, they were books written for commercial application. And if you're putting a book together to explain to people how to do arithmetic in trade and commerce and industry, a do-it-yourself, a how-to book, and these were how-to books. Most of those Arabic manuscripts were how-to books. Leonardo's books were how-to books. You end up putting hundreds of examples. Well, even the most commercially astute amongst us, even the most number-friendly amongst us, after your 10th example on inheritance, you begin to get a little bored by it because the numbers are changing but it's the same problem. So what the authors all did was every now and then they would throw in a really cute little fun problem just to lighten the load. Leonardo in his book throws in dozens and dozens of these. One of them is this rabbit problem, and that's the only connection between Leonardo and that problem and the sequence. In the 19th century, a French mathematician, Edward Lucas, who knows that that's an interesting sequence. It's the sequence 1, 1, 3, 5, 8, 11. You add the last two numbers to get the new one. It's known as the Fibonacci sequence. But Edward Lucas gave the sequence that name just to give it a name, simply based on the fact that that sequence was in the answer of one of Leonardo's problems. So, names get assigned for peculiar reasons. The only connection between Leonardo of Pisa, aka Fibonacci, the name Fibonacci is a 19th century invention as well. The only connection between him and that sequence is that it was an example in a book, among hundreds of other examples. That's it.
An interesting question here about the books. The first algebraic books were in text, where symbols were drawn in the sand. Why not draw the same symbols in the books?
Because books in those stage were copied by hand, usually not by the author. And authors very quickly realized, a lot of it was done in Europe, for example, in the monasteries and so forth. So authors quickly realized that when a book was copied, it was going to be copied quite likely by someone who didn't know any mathematics. So the symbols, even if they got copied at all, and often they left the symbols out, they would be screwed up. I mean, the symbols just couldn't survive. So authors very quickly learned that if they wanted their books to survive hand translation, they had to write everything in words. And all of that changed when the printing press came along. The printing press was, in fact, Leonardo himself was forgotten for hundreds of years, because the moment the printing press came along, one of the first books that was ever printed was a book on commercial arithmetic. It was published in Treviso, near Venice, so it's called The Treviso Arithmetic, a book on commercial arithmetic. Within 10 years of the Gutenberg Bible coming out, you have a book on arithmetic. That was how much demand there was for arithmetic in Italy at that time. It was put into print. But the moment you had the printing press, it was safe to put symbols in, and that's when you see symbols beginning to appear. And in fact, even though symbolic algebra didn't come for a couple of hundred years later, slightly less, symbols themselves appeared, and mathematics became symbolic. In fact, if you look at Leonardo's own book, the explanation, the mathematics, is the text. In the margins, you see symbolic representations. Before the printing press, mathematics was something you wrote in words, and symbols was illustrations of the mathematics. With the printing press, that flips. Mathematics becomes symbolic, and the words are what you use to explain the symbols. The printing press is what made that happen.
When do we see the first book that examines the joy and the beauty of numbers as opposed to the practical application?
That much is very much in the eyes of the beholder, I'm afraid.
Did it come across in some of the books you were talking about?
Oh, you look at some of the early Indian manuscripts. They were beautifully written in whimsical stories, often devoted to a daughter or someone. Wonderfully written, beautiful. Look at some of the early Indian writings. They are gorgeous in English translation. And the original must be wonderful. But even in English translation, they're essentially written in a poetic form. It was always there.
Question from the audience. Can we see a change in philosophical thought because of algebra, such as the influence geometry had on early Greek philosophy, like Plato and Aristotle?
Yeah, the interplay between mathematics and philosophy, they've always gone hand in hand. I mean, one of the problems the Greeks had was, there's a famous episode in the history of Greek mathematics when they discovered that what was known as incommensurables. They discovered that the diagonal of a unit square couldn't be expressed as a ratio of two numbers. And that actually caused them great problems because they essentially had a geometric view of numbers. Numbers were things that were measurements of lengths. And then when they realized that their number system didn't gel with that caused them enormous problems. And they actually they had this whole theory there about incommensurables and how you handle these things. It was philosophically very problematic. And in fact, that distinction between quantity and number, that really continued all the way up to the 19th century. The Greeks should not be faulted, the ancient Greeks, for not coming to terms with that. It wasn't until the end of the 19th century that mathematicians finally united ideas of number and quantity, because they come from different conceptions. Quantity comes from our sense of space, of length, of area, of volume. And the number system that we associate with that today are what's known as the real numbers. The integers, the counting numbers, came from commerce. So you have these two driving forces for arithmetic. One, the real world, building pyramids, looking at things moving through the sky, planning out fields. That's all to do with geometry, and it gives us what we now call the real numbers. And you have this other driving force of commerce, which gives us counting numbers and arithmetic. And they were actually in parallel, almost unconnected, until the end of the 19th century. You read Newton. Newton writes this book on calculus. Today, we interpret calculus in terms of numbers. That's not what Newton was thinking. Calculus wasn't about numbers, it was about quantities. And quantities came from the real world, and they were about lengths and areas and volumes. So when we look at the distinction I made at the beginning between the Babylonians and the Egyptians and whether they're doing geometry, those different cognitive conceptions stayed apart until the late 19th century. It was very difficult tying them together. But as always, once mathematicians figure it out, we immediately forget the history. And we forget that what was now commonplace was once taken for granted. We take Hindu-Arabic arithmetic for granted. It was a huge human advance. It's one of the greatest advances humans have ever made. It's huge. Elementary arithmetic is one of the things we can be most proud of above everything. I would perhaps put it as number one. Of all the things we've invented, it's way more than the wheel. And it's certainly more than the silicon chip. Hindu-Arabic numbers, or numbers in general, maybe numbers in general, then Hindu-Arabic, those are among humankind's most 4 or 5 most amazing discoveries. It was such a big discovery that we no longer think it's important, because it changed us from the ground up.
Well, that's another parallel to Silicon Valley, because a 12-year-old who's playing on his cell phone today has no concept that we used to stand here and say, wow, I can make the pong paddle move up and down.
Yeah, drawing parallels between, I mean, the Leo and Steve book, Steve Jobs and Leonardo, that's not the only parallel. That draws out a lot of parallels. But you read almost anything about the history of mathematics when it happened, you see it, we're living in it now. And it's just, the substrate has changed. Sometimes it was the sand. Actually, it's interesting, the substrate is now silicon. So we've gone right back to the beginnings that mathematics was done in the sand. The sand is more expensive now. But, it went from sand to dustboards, to parchment, to paper, to blackboards, to slates, to screens and so forth. And for a long time, the interface was a human interface. It was about getting arithmetic and mathematics into the head. And then in the 80s, we discovered ways of putting it into machines in an effective way. But other than the substrate and the technology, there's nothing new happening in Silicon Valley. It all happened in the 6th and 7th century, 8th and 9th century, 13th century Italy. History just keeps repeating itself. And I suspect it's going to repeat itself again.
Can we go back to your mention of the 19th century? Because that came up too while you were talking about Wikipedia. And I didn't quite follow, and perhaps some of the audience didn't as well. What is it that is outdated in Wikipedia about the topics of mathematics and algebra? I mean, to the average mind, math doesn't change. Numbers are hard. They're logical. They're solid. How is Wikipedia wrong about these things?
It's understanding what people were doing and what they thought they were doing and interpreting the text. Because, history is all a matter of interpretation, and you're interpreting things from different times. When I was writing my book on Leonardo, I had to try and put my mind into the position of a trader in 13th century Italy who'd never seen arithmetic before. I can't do that. In our world, the first thing we see when we open our eyes in the morning are some Hindu-Arabic numerals. It's the clock. That wakes us up and starts our day. We are so embedded with numerals that I can't imagine what it must be like to live without numbers. And yet that's relatively recent. So it's impossible to put your mind in these things, but a lot of the scholarship tries to interpret what people were doing when you look at these manuscripts. What were they doing? What did they mean? When we see these phrases, restoration and confrontation, many of the references will say it's moving terms from one side of an equation to another. No, it's not. That's a modern equivalent to what they did. And actually, many teachers would not use that word in the class either. Some teachers will say, no, you're not moving something from one side of the equation to another. You're adding equals to both sides. So even in modern education, you have these distinctions between what you mean by things. But when you try to interpret what people were doing in these books by Omar Khayyam and Abu Kamil and so forth, when you try to interpret these things, you're bringing modern perspective to it. Much of the stuff on Wikipedia, I think, can be traced back. There was a very influential book written in, I think, 1847 or thereabouts by a German, I think, called Nesselmann, who wrote a comprehensive history of algebra, essentially. I mean, massive. And a lot of books, a lot of the things you read, I think, derive back to that. And he was basing it on what was known and the manuscripts that had been discovered by the 19th century and the interpretations. But, scholars have been working ever since, and they've developed a lot of material. Unfortunately, the historians of mathematics, well, they haven't got a Keith Devlin or someone like me yet. Someone needs to go in, and I've started to do it, and go in and say, these are interesting stories, why don't you tell them to the world? In fact, very interestingly, the person who discovered everything that happened with Leonardo's work and why Leonardo's work was so influential, a woman called Raffaella Franci at the University of Siena, when she told me her story and said, here are some of the papers I've written. They're in Italian. Unfortunately, I can read Italian. I read some of what she said, and I said, this is one of the most amazing stories in the history of humankind. This is Galileo. Why does nobody know this story? And she looked at me and said, is anyone going to be interested? And I said, you've got to be kidding. We've got a room full of people that were interested in this. No, it's a matter of just telling the story.
Why did no one know the story? Why did it fall away? Why was it not part of common knowledge?
The historians do their thing, and it needs, and so far very few of them have started to tell the story. It really has to be a case of telling that story, getting that story out there, and it is a sad fact. It's getting to be less the case, but it is a sad fact that those of us in academia that actually devote some time to what they call popularizing, the French call it vulgarizing. French do all sorts of strange things, right? But they call it vulgarizing. Popularizing mathematics or popularizing science, until relatively recently, that was the end of an academic career. Carl Sagan was denied entry into the national academies because he popularized mathematics and he went on TV and things, and that was a negative against him. It has been the case for many years. There's still vestiges of this, that if you're an academic and you try to explain things to a large audience, that's several negative marks on your evaluation. And so there's a lot of cultural pressure on scientists not to make their work popular. In fact, I mentioned this scholar, Geoffrey Oakes, that's doing enormous work on Al-Khwarizmi in that period. Incredible scholarship. And I've been talking to him and say, we need to make this popular. I finally managed to convince him that he and I are going to write a joint book on Al-Khwarizmi. And lending my own name, I said, look, if my name's on it, people won't blame you for if it's popular. And he thought that was cool.
That's very persuasive. Well, I thought of when you mentioned that Al-Khwarizmi was told by the Caliph that he should be writing for the common person.
Yeah.
Did mathematics at any point suffer from what we've seen with other sciences, philosophy, literature, where it was reserved to the upper classes and considered too much for the lower classes?
That was definitely the case in ancient Greece. Ancient Greeks, I mean, this was the academy. You know, it was very much, and it's the basis of modern universities. I mean, the model is Greece. The liberal arts curriculum goes back to sort of Greek ideals. It was very much regarded as a recreation of the mind. In the Arabic world, the Arabic-speaking world, that was different. That was practical stuff. They wanted to do things with this. They didn't care whether you regard, it wasn't a discipline. Some of them wrote scholastic books. They certainly took influences from Euclid's Elements and Diophantus and Brahmagupta and wended them in. But they were driven by practical concerns. And they collected, the caliphs and all the wealthy people, they instituted this process of collecting all of this work together, translating the work, storing it, putting it down on paper, because it was most of this was oral tradition. They took the oral traditions, wrote them down, they translated. We wouldn't have many of the ancient Greek works if it wasn't for the Arabic translations that eventually became Latin translations from there. So it was this collection beginning in the 19th century that was done, but it was driven out of practical concerns. There was certainly an element of preserving culture, and the Western world wouldn't exist if they hadn't preserved that culture beginning in the 9th century. So there was a huge preservation going on, but it wasn't just copying and preserving and translating. It was taking that knowledge and using it for practical things. You know, they did some amazing engineering feats of building aqueducts and so forth that really boggle the mind today, and it was driven by practical concerns of engineering, trade, and commerce. And that's the legacy, the true legacy in my mind, for Arabic mathematics. It's the fact that they made this stuff accessible to all and made it useful. And modern Europe built itself on that, and the United States then built itself on modern Europe. So there's the legacy, and we are living that legacy.
Kind of very intriguing question here. An audience member who's read that there's a connection between algebra, and he uses Al-Khwarizmi spelling, A-L-G-A-E-B-R, and bone setting. Do you know anything about that?
I could make a guess, but I don't know, so I'll punt on that one.
Okay, we'll give it a pass on that. What can be done to encourage number sense in young children? There are a couple of questions that bring us into the present that I'd like to go over with you, and that's one of them.
Yeah. Well, the obvious thing is just parents and their kids together. You just use numbers all the time, and you just have number games, you play with numbers, you just reflect the fact that numbers are all around us. And they are all around us, you just have to draw attention to them. So first of all, just playing with kids and just doing number games and playing, and just making it fun. But even more, if you think about small children, they begin as mathematicians. The first things they do is they count things, they collect them into objects, they categorize things. Kids are instinctive mathematicians. The most important thing we can do is not turn them off. For many years, I taught classes at different colleges and universities, mathematics for non-science majors. So I would get the kids who really didn't like mathematics, who needed to get a math credit to graduate. And I always used to hand them a little questionnaire out at the beginning. I used to say, write 5 words you associate with mathematics, and 5 words you associate with something else, you know, something you like doing, and assuming that mathematics was not one of them. And I also used to ask them various other questions. And one of the other ones was, when did you stop liking mathematics, assuming that you don't like it? In response to the question, associate 5 words with mathematics, they would use words like non-creative, illogical, arbitrary rules. I mean, all about following illogical, arbitrary rules. It was all about it being a straitjacket, been having to learn lots of formulas. It was as if assuming that cooking was about reading recipes and not cooking food. They were locked in on the recipes and didn't realize that they were the key to cooking food. So they assumed it was, and a recipe doesn't look very creative. 2 cups of, what could be more boring? But you get a good cook. You go to Alice Waters and something and see what she can do with a recipe that's not even written down, and you realize that there's more to it than that. In response to the question, why don't you like mathematics now? The overwhelming answer was, in the X grade, 10th, 8th, 9th, I had a teacher who made me feel miserable in math. Now that's one teacher out of many, so we're not blaming all teachers, but they encountered at some point, they encountered a teacher who, for whatever reason, turned them off. And the trouble with mathematics, as it's taught at least, mathematics doesn't have to be linear, but mathematics education clearly does. When you're on that train, if you miss it once, it's really hard to get back on. And so the trick, it's not a matter of getting kids interested in mathematics, it's not killing the interest.
Well, that actually dovetails with this question. Columnist Richard Cohen has written he finds no use for algebra in his life and work. Why should we teach algebra to all high school students? Or should we?
I guess he never uses a computer or a spreadsheet. Does he not write? I wonder how he writes. I wonder if he writes on a word processor.
But he doesn't need to understand that to write it. In other words, we don't need to teach him the process of algebra.
Yeah.
So is there a valid reason for teaching algebra?
Sure. Several reasons. First of all, if you want to use any of these tools, you need some understanding. If you drive an automobile, you don't need to be an automobile mechanic, but it's useful to know you need to put gasoline every now and then, and why. It's useful to know if something happens, why it happens, and to know what to do about it. If you run out of gasoline, you know that if you go to a gas station and fill it up, you don't need to call a mechanic. You know enough about automobiles to be able to drive one safely and reasonably. So knowing something about how it works helps you to use it. We're sophisticated people, that's one thing. Secondly, as a human being, I find it hard to respect someone who wants to use something without knowing who built it, why they built it, and how they built it. That's kind of arrogant to say, I'll use this, I'm not even interested in how it works. I don't understand that at all. So, there's an appreciation for what went into something. So there's an awful lot that goes into a computer that I don't understand, and I'm not an engineer, but I know enough about how they work to appreciate them and to make me more sophisticated users. I know enough about, I know a lot about algebra actually, but to use a spreadsheet sensibly and to know what it does and to have the power of using it, whatever you're using it for, it's good to know that what it's about and how it works. So simply being a human being, a rational person, an intelligent person, to use the tools of modern society, to use them without having any knowledge of how they work, is arrogance and ignorance in the nth degree to me. I can't imagine a more ignorant statement than to say, I'm not interested in the algebra, when you're using the tools of that every day of the world. That's, not only is he ignorant, he doesn't even know he's ignorant. So, that's staggering. The other side is, it's an incredibly useful exercise for the mind. To think that the human mind finds abstract thinking really difficult. We find abstractions difficult, and yet we live in a world of abstractions. The knowledge and information are abstractions. Numbers are abstractions. Money is an abstraction. It's not coins and paper, it's purely an abstraction. And so we live, ownership is an abstraction. We live in a world of abstractions. Society is built on abstractions. And to understand how abstractions work, it helps to think in an abstract way. Algebra is one of the most rigorous ways of formalizing abstract thinking that there is. And so if you master algebra and algebraic thinking, you've become incredibly good at dealing with abstractions, and you can deal with them much more effectively. So simply dealing with the modern world is enhanced and made better and more accurate and more reliable by learning some algebra. Not because you want to explicitly use it. What he means, I guess, is he never actually needs to solve an equation because there are machines that do it for him all the time. True, but come on. None of us have enough time to learn everything.
Right.
But aren't we curious enough to want to know a little bit about everything that we use? I certainly am. And it seems to me a waste of a human brain, which is the most amazing thing, to close it off to something that hundreds of years of brilliant people have created. Doesn't he have any admiration for brilliant people over hundreds of centuries who've done this stuff, that have made his life possible. That's a weird view, quite frankly.
I want to thank whoever gave us that question.
I guess I disagree. I guess I disagree with you.
I guess so. I want to finish up. We just have time for a couple more questions here, and I want to tie this with the rest of our series. We've talked about religion in the brain. We've talked about science in the brain in earlier interviews. Talk about mathematics in the brain. We believe now, for the most part, Western culture dictates there's a left brain and a right brain. Some people can be artistically gifted, some people are numerically gifted. What does that tell us about what you've learned about algebra, mathematics, arithmetic, and how it can be taught and perceived by people?
Yeah, actually, this is going to be another book plug. I wrote a book that was published in 2000 called The Math Gene, which was actually an evolutionary account of how the human mind acquired this capacity for mathematics, which is an amazing question, because mathematics, I mean, numbers are only 10,000 years old. Recognizable mathematics is only 2,500 years old. Most mathematics is only 300 years old, which is the very end of an evolutionary trail. So the mind that does mathematics is essentially a Stone Age mind. So the interesting question is, in evolutionary terms, how did the human brain acquire the capacity to do mathematics? And it's what Stephen Jay Gould used to call an exaptation. It's taking capacities that the mind evolved for other purposes and remixing them to form this thing that we call mathematics. And one of the things that came out of that study was realizing that mathematics is just a twisted form of language. Language, ask yourself why or how language evolved. Language clearly did not evolve to communicate, because we couldn't communicate with language until we had language. So there's no natural selection to do it there, right? So if you ask how language came about, and then linguists do ask this, you end up with the story that language came out of the articulation of a capacity the brain developed for thinking about the world. One of the things that distinguishes humans is we can switch off the inputs, switch off the outputs, and run simulations in our mind. We can plan, we can do what-if scenarios. We can say, how can I handle the fact that there's a couple of saber-toothed tigers over there? Let's plan and coordinate. Human beings learn to survive by thinking offline, by using the brain to run simulations. Now, if you're running a simulation, one way of describing that in terms of expressing it is you've got grammar. Grammar is a structure that got into the brain when it learned how to simulate the world. So language, and it was immediately used for communication, because once you've got a brain that can think complex thoughts, then you can articulate the thoughts. The reason communication can't be the driving force is you don't need language to communicate. We can all go to a foreign country and we can gesticulate and get our wishes known. And humans were communicating for 3 million years. Much lower than that. I mean, but anyway, let's just take 3 million years for Homo sapiens where we were communicating. We only got language maybe 200,000 years ago. So language is very recent. And it was certainly not built by communication, because communication doesn't require language. It requires just gestures and words. You can say hungry, danger, but you don't need a grammatical structure. So for millions of years, our ancestors communicated by single words and simple me, Taz, and you, Jane sort of things, and that gets you by. But the moment you have complex thoughts that involve planning, looking ahead, you can't use gestures, because it's no longer in your environment. It's a different environment. It's what-if scenarios. So the moment the brain starts thinking and planning, the only way you can start communicating with each other about your plans for the future, your deconstructions of the past, discussions about a different location, then you need a lot of structure. You need to articulate that planning structure. That's grammar and that's language, but it's also mathematics. So mathematics itself came out of that same capacity in the brain that gives us language. Why didn't mathematics come immediately onto the scene when language did? We know that language began, it could be as recently as 50,000 years ago, grammatically structured language. Could have been 200,000 years ago, maybe even 300,000, but relatively recent. And yet, as soon as language comes on, as soon as the brain learns to articulate this planning capacity, it starts getting used. And the point is, communication was the killer app. Once you've got it, you're going to use it. Society wasn't ready to use the numerical version of language, which is arithmetic and mathematics, until around 10,000 years ago, when the Sumerians needed money. But the moment they decided their society needed money, it came right out, because the brain was ready, because it was just language. So it's just a different expression of the language capacity.
This has been fabulous. I wish we had more time. Thank you so much.
Okay. Yeah.